It's okay.
It's going to be amazing. Yes. It's going to be amazing.
That's probably enough drinks for tonight.
That's so cool. It's going to be amazing. It's going to be amazing.
That's probably enough drinks for tonight.
Yes. That's so cool.
It's okay. It's okay.
Yes. That's so cool.
That's probably enough drinks for tonight.
That's so cool.
It's okay.
Yes. It's going to be amazing.
It's okay.
Yes. That's so cool.
That's probably enough drinks for tonight.
Hello, everyone. Thanks for joining us on another stream. I'm Mario Garcia, Technical Evangelist at Percona, and today we have Charlie Batista, who is Postgres Tech Lead at Percona, and he will talk about using Postgres and Redis to boost performance. Thank you, Charlie, for joining us today.
Hey Mario, hey everybody. It's great to be here again. It seems like we haven't been here forever, right? So it's been a
Yeah,
few weeks we didn't do a stream, and it's really great to be here. And today we're talking about an amazing topic, right? About caching and the database. Well, as you mentioned, the topic today is about Redis and PostgreSQL. But before we, oops, I have a problem with my chair. Man, I almost felt alive. That would be awkward, you know, really awkward. Yeah, as I was saying before, we go to talk about Redis and Postgres. I would like to take a little bit look at memory and caching, right? To understand what is caching and how that can benefit us from having a better caching subsystem, even on the database itself. Because I've often seen people misunderstanding how database pull data from the storage and put in memory, and how that can be optimized even without using third-party tool like Redis. And there are other tools actually. For example, the old memcached, people still use them. It's still a good tool, depends on the circumstances. We also have connection pooling like PG pool that also offers a cache layer, right? We don't have only one tool that can be used. And understanding how the database works, how the data moves around probably will help us to understand which are the tool to use, when to use, what are the circumstances, right? I think that would be a good thing. And by the end, we will talk more specifically about Redis and what are the benefits and things that we need to plan to think about. Some shortcomings because well, there is no perfect tool, right? There's no any perfect solution. All solutions they have strength and weakness, the same as Redis. There are cases and circumstances that it's better not to have them, right? So let's start here. I would like to share my screen. To share screen here, share screen. Yep, I want to share my screen here. We can see my screen, right?
yeah,
Okay, great. So here, what we have on the left some slides of the presentation that I've been giving since like 3 4 years now, and on the right side we have some SQL scripts here that I'm gonna use to walk through on what I want to show today, right? So the first thing that I want to talk about is memory architecture. So it's very important to understand how the memory architecture is organized and actually what is a cache, right? When we talk about cache, what exactly is cache? What does Redis do? What does other tools like the memcached or even pgpool they do when we're talking about caching, right? So one very important thing that we need to understand when it comes to computers is things they get expensive as they get faster, right? So and usually when we need to store a huge amount of data, we choose cheaper devices because we will favor more space than speed. If you see here on this diagram here, we have on the bottom here magnetic tapes. Like people may still think, oh, does it even exist nowadays? Well, it's an old slide, but bear with me. It still does. There are some people out there they still use them for backups. You know, it's I don't think it's super common on Postgres vaults, but other database they still use them as a backups because They can hold a huge amount of data and a very low price. It's super cheap. But the problem is they're super slow. They're really, really slow. The type of I/O it's sequential. It can only do one I/O at a time, and sequentially. So that makes it really slow. So the next one are the old magnetic disks, right? The hard drive, the old hard drive. They are also slow, but they are a lot faster than magnetic types, especially because of the way they are designed. So when we have a magnetic disk, we can have more than one head that can read data at the same times. So the amount of heads that we have on those magnetic disks, we can create queues for them and queuing up IO requests. So if we have like 5 heads, very expensive hard drive that has like that many heads, and we can have like 3, 4, 5 queues on those ones, right? But usually we only have one queue because, well, one head. And people often think that the problem about the performance on magnetic disks are the speed of the disk itself. Well, that's half true. When we have a faster spinning disk, we obviously make sequential I/O a lot faster because, well, you just put the head on the top of the disk and it's spinning. The faster it can spin, the faster we can read. That's fine. But the biggest problem are about random I/O because the head, we have the spinning disk here, and the head needs to keep moving. And this movement of the head is super slow. Even if compared with the spinning, it's really, really slow. This is what makes random I/O super slow on my magnetic disk, right? So we have now the solid disks. They are not here in this picture. They would be between the magnetics and the main memory. So as the name implies, they do not have moving parts. They're solid. They look like a main memory. Let me see if I have. I don't have any picture here. Oh, so bad. But they just looks like a main memory, a main chip of memory, right? But the components they are built a bit cheaper, and the way that they're organized, they're built, is a bit different from main memory because they need to persist the data across shutdown. So even when we shut down the box, when they lose electricity, the data needs to be persisted. So they are slower than main memory, but a lot faster than magnetic disks. And because there are no moving parts, because there is no, this head doesn't exist in there, so we can organize them in a way that we can have a lot of I/O requests at the same time. So one of the problems of the magnetic both disks and tapes are because there's mainly sequential devices. So when we put, for example, on the magnetic disk, when we put the head, the disk is spinning. We need to wait for all that spin to finish the read, right? So, and if we have one I/O request, there is no way for the head to keep moving to service different types of I/O, to do parallelization of the I/O, because we have only one head. And this makes things a lot slower. On the other hand, on the solid disks, we can organize the components that they can process different I/O requests in parallel. So despite of not having the moving parts, just this parallelization of the I/O requests, they make the performance a lot faster. So there are a lot of gains, and now the random I/O is not so expensive anymore. So it's a lot better, a lot faster to do random I/O on solid stock disks than on magnetic, because you can parallelize them, and we do not have the head. However, random I/O is still a bit slower than the sequential I/O. But the difference between them and the magnetic gigantic, for example, random I/O on magnetic disk can be like 100 times slower than sequential I/O. All depends on this even more. Random I/O on solid disks are not that huge difference and more. Probably depends on the device we have, on the disk we have. We can have like 2, 3, 5, 10 times different performance. But if you get those 5 times, for example, different performance from random to sequential, and compare to 100 or even 200 times different performance on magnetic disk, it's a huge improvement. So, but they are a lot more expensive. They're getting cheaper, but they're still more expensive than magnetic ones, right? And then we have the main memory. So here, the things start to be a bit faster and in another level, let's put on this way. So the main memory, it's faster than magnetic disks, but it cannot keep persist information when it loses power. That's the main problem when it comes to main memory, to RAM. As soon as it loses power, the information is gone. It's also a lot more expensive than magnetic disks or even than solid hard drive. So if we can pay, like, for example, a cheap solid hard drive of 1 terabyte, around $100 for 1 terabyte of main memory, that's gonna probably cost, I don't know, probably $1,000, maybe more. So, and the price difference is still huge. So if we have 1 terabyte, like this 1 terabytes data, it's for database, it's getting like nothing. So we're going through database like with hundreds or even more terabytes of data. That would be amazing if we could get that 100 terabytes of main memory, right, to process everything in memory. But it's super expensive. It's really expensive. And then we get to cache memory. So the cache memory is a chip memory it's built inside of the CPU sock, the CPU chip. So the whole chip inside, we have this block of memory that is cache memory. This is super fast. It's really, really fast. It's a lot faster than main memory for mainly 2 reasons. The components that are built are different than main memory and a lot faster. And also it's a lot closer than the CPU itself. So it's on the same chip. So the path that information needs to travel from the cache memory to the CPU, it's really, really close. It's really small. So, and we'll see that makes a lot of difference. It really does a lot of difference. And because of it's so expensive, the cache memory usually really, really small. And one thing that we need to understand is when the CPU is working, it's the data actually that CPU works, it's stored in cache, and then they've been worked by the register. The register are the tiny blocks of memory that built inside of the core, the microchip, the processor, not only the chip itself, but the processor itself. So there are tiny blocks of storage that being used by the CPU. Actually, they are the ones that do the work. So we have register to store data, we have register to do operations and to store instructions. They're tiny, super fast, and super, super expensive, right? And the register is probably like, I don't remember top of my mind, but they can be like 50 or 100 times faster than cache memory. Cache memory is probably around that to main memory, and that's so on and so forth. And one thing that we also need to understand is there is no physical connection from the CPU to the I/O devices, like for the hard drive or for the solid drive. So literally, there is no cable. There is no physical cable from the CPU here to those storage types. And that's one reason why you really need to work through memory, because every information that the CPU needs, it's gonna ask the memory. And that information needs to be loaded from the hard driver or the solid driver to memory, and then the CPU can access that information, put the information inside of the cache, and then works with that information from cache to the register. Because if compared to the CPU, the main memory is still super slow. So the main memory, RAM, even though it's a lot faster, it's still a huge storage area for the CPU that it needs to go there on a slow place, get the information, put back on a storage that's faster, like for example the cache memory, and then it can be worked by the CPU, right? So basically, cache is a faster area that we store data. From the CPU point of view, cache is this memory that's inside of the SoC, the CPU SoC, that stores the data. Well, but what is cache for the database? On the context of database, what is a cache? Well, to answer that question, first we need to understand how the database stores the data, right? And that's why we have this thing here. The data is stored by Postgres. They're stored on what we call heap files. So heap files is just a form or organization of file, and it's one of the simplest form of organizing a file. We basically put blocks of information one after another. There is no logic, there is no science on this. It's just put one block after another block. As simple as that. Let me see if I have. Yeah, that's basically here. It's a heap file. So we have block 0, 1, 2, 3, and there are no special relation between block 0 and 1, between 1 and 2, and so on and so forth. The only special thing that we have are inside of the blocks, how those blocks or pages, depending the literature we're using, how they're organized, right? So how they're organized internally is the only thing that makes them special. But like for the organization, there's nothing special on a heap file. It's just one block after another. And one thing that we need to understand is every time that we insert or update something inside of the Postgres, it will always put the new data in the end of the file. So there are other forms of organizing files. For example, we can organize the file just like AB3. That's a common file organization when we are using a cluster index, for example, MySQL InnoDB that uses cluster index by default. It's just organized file as a tree. Let me see if I have, yeah, sort of something like similar like this here. We have a tree inside of the file, and this is how the cluster index organizes the file. But Postgres doesn't organize like this. Postgres is just put one block after the other, and there's no special relation or meaning between those blocks, right? This way it makes super fast to write on Postgres. That's why it's faster to write, because we always put in one block after another. We never need to reorganize the file. For example, on the cluster index, if we change the ID of the index, we need to reorganize everything, because, well, that value that was in the index, it now needs to be put in another place, and then the whole file needs to be reorganized again, right? It's not necessary on the heap files, on the Postgres data files, right? But then, yeah, it also makes a lot faster to do full table scan on Postgres. Remember that I mentioned that sequential scans are a lot faster, sequential reads on disk are a lot faster than random reads. So if we have the file that always appends, that we do not have any specific type of organization like AB3, we can just do a sequential access, a sequential read. Get block 1, block 2, block 3, block 4, block 5, and so on and so forth. We just read through the file and we get all the data. That's all we need to do a full table scan on Postgres. On databases that uses the cluster index type of organization, because they organize the file like a tree, the block 2 might not be just close to the block 1. The block 2 might be further into the file, and so on the block 3, and the block 4, and the block 5. So when we have an index that's organized as a B tree, we just change the access inside of that file from sequential to random access. And that's why it's so much more expensive to do a full table scan, for example, on InnoDB. Because InnoDB organize the file internally as a tree. So the blocks, they might be far from each other, and then we are doing a lot of random access on those files. And when we do, for example, a select start from table A, and we do not have any where clause, it's super slow because it does that so many random access inside of the data files. For the other hand, Postgres is just read through the file, and it's a lot faster, right? So, okay, now we know how those things work. Now we know how Postgres organize those things. But another important information, and that's for all databases, not only for database, but for operational systems as well. The operational system doesn't read bytes from the storage. So when we open a file and we ask the OS to read that file, the OS will always get one block from that file. Doesn't matter if I open this file here and I only need this first line here that has 16 characters here. So it will read the whole block. So I have 16 bytes here. But what's gonna be given by the OS, by the kernel, by the IO subsystem, gonna be 4 kilobytes block worth of data here. And this also happens for the database. When we go for Postgres and we do, for example, here, let me just create a table here. Okay, I want to disable auto vacuum. Don't do it in production. Never disable your auto vacuum. I want to disable here because it messes up with what I want to show. But never do that on production. Never disable auto vacuum on production. Right? I'm gonna create this table here. I'm gonna insert 1,000 rows. I'm gonna push to the disk doing a checkpoint. So for now, I don't really need those things, but okay, let me do read those extensions because they're quite useful. Okay, I have this table here, the T-heap, and this table here, it has a few blocks because, well, I inserted 1,000 rows here, right? I have a few blocks. If I do a select, it starts from T-heap limit 1, oops, yeah, it will give me only 1 row. But actually, the database put in memory the whole block, the whole page here. The whole page 1, page 0 here that I have. So we have some hidden data here. The whole page 0 here that we have is being put in memory. So this page is being cached. Basically, this is what it means. So it was in disk, it's being read from disk to the OS cache, and then from OS cache to the Postgres cache or Postgres buffer, right? So it's been done. Now we have this here in memory. If I do the select again, let me do one thing here. I think it's timing. Yeah. So if I do the select here, it's gonna be increasingly fast, right? So that's it's super fast. If I go here and do a restart on my database, I hope this one. Yeah, I just did a restart on my database, and I let me do the timing, and I do the select again. Look, that took a lot more time to grab the information out. Because now it needs to go to the disk. I just restarted the database, I cleaned the database cache, so it needs to go to the disk to get that data and bring back to me. Right? The first time we access it goes to the disk, to the I/O subsystem. Now, if I do it again, so now it comes from the database cache. So the database itself has internal cache, just like the OS also has internal cache. So a cache page, the OS, in my case Linux, it's caching pages. The OS doesn't care what's the information inside of that page. The only thing the OS knows is that I asked him to read one page, in this case the page number 0, from that file. In our case, let's get the file here. So let's show the data directory, and let's get the folder name, and then let's get the file name. So how Postgres organize information, it's interesting. So this is my data directory. So if I go to my data directory, here, inside of my data directory, we're gonna have one folder that is named base, right? This is where all my data files, they are stored. But their names, they have numbers. Those are object identifier, or OIDs, as we call it inside of on Postgres terminology. Right? They are object identifiers. The files and the folders and everything inside of the data directory on the base one, they organize it like this way. So my database has this object identifier. Here I can go inside of my database, is a folder, and here I have few tables, indexes, and other files that's for the database organization. And this one is the table that I just created, theap, right? So I can check this table. It has 56 kilobytes. Well, we can do a simple math here. Postgres uses 8 kilobytes for page. So if it has 56, so we have around 7 pages, 7 to 8 pages here, because, well, it's more than 7, it's 7 pages here, because it might not have been written all the data through all the pages. But we can do a nice thing here. If we remember that I mentioned that the Postgres doesn't do any fancy thing. If I do the select here, okay, I want to do the select from the table. So this is the data that we have here inside of my table, right? So I can go inside of that file and check my data here. Actually, let's do that. So one thing that I'm gonna do here, okay, let me get the size and the position that we have here in this table. So I have a few examples here. Okay. Where is my XDump? So,
Charlie, there is a question.
yes, please.
Yep. Can we purge single query from the database cache?
I can elaborate a bit more on the question. Can we push a single select from the database cache? I didn't really understand what if who asked the question, Mario?
Amit, that
Amita, could you elaborate a bit more on that question? Like give an example or something because I got a bit confused by your question. So, but while we wait for him to elaborate on the
okay.
question, one thing that I gonna do here is I will do a where clause or ctid.
Yep. Okay. He says, is it possible to flush a single query from the database cache?
No, actually, we don't have manual control over the database cache itself, right? So the database organized how it cleans up the cache on the database. Most of the database, including Postgres and MySQL and other open source database, they use the what we call LRU mechanism that the least recent usage. So we are putting like all the selects that we are doing here. We are everything that I select that is a new data will be put in the database cache, right? So we have a limitation on the cache. In our example here, let's go here. Let me see what is the size of our database cache. So here I have, this is my database cache for queries, the shared buffers. I have here 8 gigabytes reserved for my database. So Postgres will use 8 gigabytes to cache in operations. The operations can be selects, the inserts that we do, like the first time that I did that insert, it first goes inside of the buffers and then it's being flushed. And so when we start working with the database, this caching is going to start being filled, right? Eventually, we will fill all those 8 gigabytes. So when we have a new thing that comes to put inside of the database cache, it needs to clean some space. So the database will check through everything that's been there. It has a list of the objects that's being used, and inside of the list we have information from when was the last time. So when it's being, we put in more things, we put on top of the list, right? Let's think about a stack. So we are stacking things on top of the stack. What is on the very top of the stack was the objective that being used more recently, and it's on the bottom of the stack are the objects that have been used long ago. So what the database does is, okay, it's just remove that one or clean up that space, move things down, and then we put something that new data. So the database does automatically. Probably one thing that Amit want to do to clean up is, okay, I just did the select here, right? So I don't want to run the select from the database cache again. I want the database to go through the table and get that information back. So is there any way that I can ask Postgres to just remove this instruction from the cache Like I go there and ask, no, there is no. We don't have that instruction. Not from the database itself. Might have out there an extension that help with those things, and I particularly not aware, but I'm not that might have extensions because we have extensions for really nice extensions for Postgres to inspect the shared buffer. So we can go and see what's inside of the shared buffer and inspect the things that are there. So they're very helpful on troubleshooting some certain of problems. I do not advise to have them on production because they might cause some problems. But if you have a problem on the database that we want to inspect the shared buffer, yeah, there are extensions out there that help us to inspect the shared buffer. And to clean the shared buffer, I'm not aware of any of them, but maybe, might have one extension out there. Does that answer your question, Amit? If no, send us back something. If yes, just give us a thumbs up there. All right, let's move because it's 30 minutes already. So one thing, okay, what I was doing is, yeah, I wanted to inspect here. So the select that I'm gonna do here, it will get all the, oh, actually I want to, it's not the only one, like, does that work? CTID. No, I forgot how to do that one here. Okay, I gonna do a workaround here. Order by a mask. Limit 100. Yeah, we have 7 pages, but obviously this is not what I want. Heap where CTID were a smaller than 100. Okay, not yet. 120. Okay, let's start being lazy. Let me get here. What I want to try to do here is to get the last object inside of my page. So I'm going to the page 0. And I want to get the last object here. So I have this here. I don't want to create an index. Okay. Let me go to the top. Oh, that works. Click in the front here. Okay, this is my whole page, page number 1. So this ID here is the last one that I have in this page, right? So if I get only this guy here, where A equals 157, so this is my last row from this page. This is the last row that I have from this page here, right? So if I go on this page here, I can actually use this nice tool here. What is the page? This is our ID, right? So, and check the information that we have on the page. So how does it work on Postgres? When we insert data on the Postgres, the internal layout, the data that is being inserted inside of the page from the Postgres, they are inserted from the end towards the center of the data, the page that we have inside of Postgres. If I get here, let's see what X does, right? Let's do a help to see which what all each parameters. So here we want to print the information as just ask, to display them as ask. That's fine. The dash n here is this the amount of data we want to pull to show. I only want to show 70 bytes. And here the dash s is the place I want to start. It's like I'm skipping 8,120 bytes. So starting from 8,120 bytes, I'm going to the end of the file here, right? 8,000. I want to read 72 bytes from this file and display this information as ASCII characters. So because we have that 157 rows inserted in this file here. If we start, let's start here. Let's put 100 bytes starting from the beginning of the file. What we'll have here, okay, we have the header. Let's do a bit more. Let's put 300 here. A bit more, 400. Okay, now we are out of the header things. So this is after the header, what we have in the beginning of the file, right? So we have those here, we have the headers and the pointers. I'll explain what that means. But the beginning of the page here that we have the information, we have the last ones. That's why I wanted to check what was the last information. So we see here, this is inside of the data files. We have the row here, number 157. So if we do the select here and get the row number 157, see, it's pretty fast. If we go for the row number 17, it will also be pretty fast. If we go for I don't know, number 1, it's super fast. 100, around the same milliseconds. So this time it's spent more going through memory to find the data and display the information here than really selecting the data, right? So we still have some time to spend with query optimizers or internal things, but the data, this whole page here is already in memory, it's been already cached on the database. But okay, why is this so important to understand this concept that the database always bring the whole page here? So in everything that's in the page, it's being cached on the database. How does it change anything from, for example, my database design? Well, that actually changed a lot of things. A lot of things. We can design our database to use the cache better. For example, let's say I have a user table, right? I have this application that I have the user. The user has his ID, username, password. That's fine, and also has address, has phone number, has security, social ID, and a lot of information. So let's say I put 20 rows, 20 columns on my table, right? So we have ID, let's say we have ID, we have name, we have email, we have name, we have password, we have address, and phone number, and I don't know, a lot more information here, right? So let's say here we have 20 columns. Every time, every time that user goes to our application and has the nice form of username and password, just to validate that username and password, we put all this data in memory. It's waste of memory. What if instead of have this huge table, I have one table user, right? So where I have the user ID, maybe the email if you use the email as a username, and the password. And then I have user attributes. And then obviously we have an ID here because the same ID as the user. We have name and everything. Just changing this design here in this very simple example, I can optimize a lot more my application because now I'm gonna put a lot less information on memory. Remember that the whole page goes to memory. And an interesting thing is if the user ID, I don't know, number 100 does a login, and then the user ID number 157, in our example, does another login, and the user ID number 17 does another login, and the user ID, I don't know, number 69, it's not a good number, 73 does another login. All of them are now in cache, in memory. And because our table has fewer columns and those columns are smaller, we probably can put a lot more information inside of a single page. And having one single page in cache, in this example here, could service 5, 10, 20 different users. And that boosts performance. Because the database doesn't need, in this circumstance, in this example here, to go to the disk anymore. And that improves performance. That boosts performance. Because we are improving our database design here to make usage on the cache, on how the database cache works. And that we can leverage even more because, okay, now we're talking. Today's talks is about an external tool, Redis. This makes easier for us to make a better usage of Redis, for example. Because we start segmenting the data. Data segmentation in these circumstances can give us a huge improvement, a huge benefit. I've seen out there people creating tables with hundreds of columns. Well, obviously, depending on the design of your application, like if your application is not all LTPs, it's more all app application, that obviously makes a lot of sense because you do need to use all those data when we are using the table. But if your table is gigantic, it's massively huge, and you make use most of the time of 3, 4 columns, it's a waste of memory space. You are wasting memory space. And even the caching that you can put on top of the database, they can suffer a lot with those things. Right? So understanding how those things work, how the database organize and put those things, help us also to work with those things. Right? And okay, let's talk a little bit about Redis. Well, Redis is a first in-memory database. So despite of a lot of information that we see out there, Redis is not only in memory database, it's mostly memory, it's memory first, right? So everything that Redis does, it puts first and tries to keep in memory. But it's also the data structures that Redis has, it's been saved to disk, right? So it's a very efficient and fast caching database, like we can use for caching. And it's been highly used for with database like Postgres and MySQL. So there are basically three ways that we can use Redis with Postgres. We can use the read through. So every time that we access data on Postgres, that data that's the application access on Postgres is being then cached on Redis, and Redis will try to keep the data that's most used and on its cache, right, on in memory. So then the application tries to go. It goes to when it goes to the database, it passes through the Redis. If the Redis has this information, it will serve the application. So the application doesn't need to go to the database anymore, right? So this is probably the most common use of Redis with the database. So you check if Redis has information. If Redis has information, fine. If not, so it reads through and goes to the database. So the other alternative is write back. So when we write the information, the application can write the information to Redis, and then it's gonna write back to Postgres later. It's later on being written to Postgres. So it improves performance a lot because, well, writes a lot faster. Writes, its main purpose is to be fast. The problem about this approach is we lose in reliability. So if we have a data set, if we have data that, yeah, we can lose some of that data, it's fine, it's okay, we don't need to strongly enforce the persistence of that data. So that's a good approach. Use write back. So it's been written first for Redis and then later for the database. Another alternative, the extreme one, is to cut off Postgres entirely, right? So depending on your application, for example, if we're using for caching cookies on a website, well, we don't really need to write it back to the database, right? So we can only keep those things on Redis. So then all that information is being just written to Redis, and nothing goes to the Postgres. That's really fast. So, but what's the best approach? What's the approach that works for us? Well, it highly depends on our needs, right? So if the data is important, we really need to keep that data. Well, probably the best one is to read through. We have Redis, just a caching. So all the information passed through Redis and then reach the database. So it's saved, it's persisted on the database. And next time that application comes, the information will be there. It's on Redis, right? So, and it doesn't need to go to the database anymore. It's really fast. So if we have something that, yeah, we can lose some data, is not that so important, write back, it's probably a best option. And circumstances like the example that I gave for cookies on a website, we don't really need to save that information on Postgres, right? We can just use Redis at all. And nothing goes to the Postgres in these circumstances. But one thing that we also need to keep in mind, and it's very important when designing an application, is every time that you use cache, we have this problem of cache invalidation. Cache invalidation is a very complex problem, and we depends on how we do the invalidation of caching. We can have stale data. Like, for example, the application doesn't get the most up-to-date information. It might happen that we get an information that was updated a few seconds ago, right? And that's very important point for designing application. How are we gonna do the caching validation? Is the application that going to do the validation? What is the approach to do the caching validation, right? So those are important things, really things when it comes to use Redis. Well, for the talk today, we don't have time. It's not actually the purpose for us to go there and install and those kind of things. And for those, one thing that I'm planning to do is I've been selecting some topics that we've been discussing here on those calls and things, and I want to later to organize some labs, right? So gonna be some sessions that we go. It's just okay. Gonna pick the topic, for example, Postgres and Redis, and go and do some lab. Okay, we go to install the Postgres, we install Redis, we build a simple application, and to see how those things work using, for example, Python or PHP or Java or even pure C, right? To do a walkthrough, a lab, and to see on real time the problems that we might have, right? So let's break the database, let's break Redis, let's break Postgres, let's see how that works with the application. This is one thing that I'm planning to do. I've been thinking about those things for some time now, and probably starting next month I'll have a bit more time, uh, and I'm organizing. So if you guys there have topics that you'd like to go through, that we go like more really deep hands-on thing, right? We're breaking things and having some fun together. Yeah, just put on the comments or drop my message on my LinkedIn there or my GitHub, right? Even on Twitter, or I still have. I think I don't really use much Twitter. I a bit unsocial for those things and not really social there. But yeah, drop some message. Let's see what you would like to go through. Like we've been talking about a lot of things, right? We're talking about query optimization. We've been discussing about replication, high availability. I think high availability is really a great topic. I would like to go and build one cluster, two clusters, put those clusters to work together, break one with the primary, and then break the cluster entirely to see if the other one gets back in replication, right? What the problems can we have? I think it's a great topic and gives a great walkthrough. But yeah, send your comments, guys. It would be really good to see what you are up to. And so we to start to go with like more hands-on talks. We're not stopping with those talks. Let's make it clear. We still have a few topics to go up to the end of the year. So we still be here. And the idea is to have another session at another day. And so that we like just going through and seeing those things and sometimes making, failing, breaking, and rebuilding to see how things work out there. How is the DBA live? When we go for production, okay, what things funny and fancy and annoying sometimes we can say. And that's it. We're on top of our time. So we have more questions, Mario. Anything from you?
Yeah, not any questions in the comments, but I think it's an interesting topic, and it would be really interesting to see a real example of how to use both technologies to boost performance. But and also, as you mentioned, if people who are attending these streams are interested in learning more about a certain topic, please let us know on LinkedIn, on Twitter. I just put in the screen our Twitter. Yep, you can contact us there. So
Yep.
please let us know. I think there is no questions, but if you have any other question after our stream, just contact us or leave a comment in the stream.
Awesome. Thank you, Mario. Thanks, guys. Have a great day.
Thanks, everybody. See you on our next stream.
Bye bye.